So maybe you get a mathematician, probably seen in some form or the other, right? Which is, so a very, very fancy version of dimensional analysis is what is done when people do wind tunnel testing for plane, for aircraft and stuff. Because what you're trying to do is to use a mock-up, a model, and you are using how the model performs as a way to figure out how the actual thing will perform in the real world. And the claim is that the similarity between the model and the reality is enough to give you useful indicators. It won't be obviously the exact thing, but it will give you a way to tweak very important variables. And then you can do much, much more refined things. Incidentally, there is the one dream of data-driven work, which I think will never succeed, is get rid of all this. Meaning, if information processing and memory and data are essentially infinite and free simultaneously, then why do all these controlled experiments when you can just crunch the whole thing? But I don't think the world is unfortunately too big even for the biggest computer. But if you know your basic physics, the trajectory of the bob satisfies a certain law, right? The time period is broadly around 2 pi under square root of L over G, right? For small theta, meaning that if the angle here is small, which is under what's called the linear regime, the nonlinear pendulum is very, very hard to actually solve. You know that it's, broadly speaking, square root relationship. And what's interesting is, you can get that, apart from that 2 pi factor, almost for free. And that's what dimensional analysis does for you, right? Which is that assuming, so this is where it becomes interesting, assuming that the variables that matter. Now, a pendulum, even with a spherical bob at the end, could have zillions of variables that could affect it. So for example, it's possible that rainfall in the Amazon forest tells you how much or how long a pendulum would take to go back and forth in Bangalore. I mean, that's the famous butterfly effect, right? But the assumption of linearity, which is why. So once you say that the world is linear, so that's a kind of dimensionality assumption. Right? It's saying that most things don't matter, and even the things that matter only in a linear way. But as soon as you say that the world is linear, it immediately says that there are certain discrete dimensions, and a small number of them, which are the only dimensions that matter. So what would that be for a pendulum? Well, you can imagine that the length of the pendulum is potentially a variable that matters. Gravity matters, right? But as you know from Galileo's famous experiment, the mass is not the issue. It's the acceleration due to gravity. So the g plus this here matters. And what else? Potentially theta could matter. Okay? But you can empirically figure out that it doesn't. This is again what, sorry. Okay, so if you empirically figure out that theta doesn't matter, right? So Galileo was the first person to see that, right? That the pendulum's the time period doesn't depend on the actual angle. As soon as you know that, you can get this square root relationship for free. The reason being, what combination of L and G is going to give you time? The L is, of course, is an independent dimension. It has dimensions of L. G, if you know your internal physics, is really acceleration, and therefore that is L over T to the power 2. So how do you get T out of something which is made out of G and L? Well, you divide L by G and take the square root. So what this is saying is that if at all there is any relationship, it must be this one. So you get for free, apart from that factor of 2 pi, exactly the relationship between the length of the pendulum and the period. Right? G again on Earth is fixed. So basically what this is saying is that square root of L is the real factor. Okay? Because L is the only thing that will change here. So that's, you're getting a time period of a pendulum. And incidentally, this square root, this 2 pi, right, can be figured out empirically. Meaning that now that you know that the pendulum must be a square root of L over G, you can use the pendulum's amplitude to figure out what pi is. Right? Because you know that it's some constant multiple of square root of L over G, and therefore if you actually figure out the time period of the pendulum and divide it by square root of L over G, the answer that you're going to get is 2 pi. And therefore one very interesting way to find out what pi is to get that. Okay. A more maybe data, a kind of problem that we might care about a lot if we're doing reasoning is what's called, I'm going to call it the surprise lottery. Meaning, suppose that you're in a room with, so this is you just imagine a TV show. So you are in this TV show, Kaun Banega Crorepati, volume 7 or whatever, right? There are 3 doors, and you are told that one of those 3 doors contains a crore. Hopefully in, let's say, 1920, when 2020 when it happens, a crore will be worth something. Right? I saw there's this great picture that one of my friends put up on Facebook, right, which was a Zimbabwean note for $500 trillion or something like that, and you get it probably not very much. So, be that as it may, like nobody talks about Lakpatis anymore. So, Crorepati still seems to have some cachet, but Lakpati is gone out. So, but there's a crore of rupees behind one of those doors, the other 2 have nothing. So you are asked to make a choice. You point to one of them. So you point to, since they are arbitrarily called, let's say you point to A. You say, I want to, I'm choosing A. So the, let's say usually these shows have some attractive blonde or whatever woman, prancing around, right? She comes and opens B. Opens it and shows that B is empty. Okay? So then the presenter again asks you, do you still want to keep to A or should you switch? Okay? Now what should you do? You should switch. Okay, how many of you just know the answer? Okay, that's cheating. Right? Because first of all, I don't care if you know the answer. If you've done the reasoning through some lots of number crunching, I don't care. What this is about is how to get to the answer, right? And how do you get to it? Purely on rational grounds. Okay, meaning if you can put a probability measure, so which is to say that there is, right? So in one way to think about it would be that in the absence of any information, it's 1/3, 1/3, 1/3. It's evenly distributed as far as you are concerned. Remember that the presenter always knows the answer. So this is an asymmetric, it's a game of asymmetric information where you are playing against somebody who knows exactly how the world is. Okay? So as far as you are concerned, and as good Bayesians, we only work on the things that we know. Right? So as far as you are concerned, it's a flat distribution, 1/3, 1/3, 1/3. Incidentally, it is already saying that you are putting a number on the world. Right? So and what I'm saying is that as soon as you are capable of putting numbers, you can figure out the answer to this problem. So assuming that numbers can be put, how do you work your way backwards to solve this problem? Okay? So Bayes' rule, which basically allows you to invert, right? See, what you know are the probabilities, right? So if you think of A as the probability, so if you, I'm just reading it out over there. So probability small a is the probability that the door you picked is good, and probability of B is the probability that if you pick the door B is good, and so on and so forth. Right? Now, probability big B is the probability that the second door is bad and gets opened. Okay? And what you want is probability A given B. Meaning, what is the probability of the right door number A being the right door, given that B has been opened and shown to you to be wrong? Right? And Bayes' rule allows you to invert that. It is basically probability of B, which is the door being opened and being wrong, given that A is true, times probability of A divided by probability of B. This immediately comes from saying that probabilities obey numbers. That's all. Bayes' rule is nothing but how do you calculate probabilities given that they are represented by numbers. Okay? Which you can then expand. Now, initially, as you can see, in equation 1.11, all the probabilities are flat. Everything is equally probable. But as soon as you import this extra bit of information, which is that the probability, right? That the presenter knows the answer. And therefore, which is to say that probability of B given A therefore becomes half. Right? And as soon as you have that, you can invert it and you can get the answer of that as 2/3. Right? Meaning that as soon as you know, so how do you implement the probability that the presenter already knows the answer? Right? So there is no chance that they would have opened A itself. Right? Because if they opened A, then they have actually, then they have ended the surprise, right? Because you pointed to A, and if they had opened A and it was empty, then they have just solved the, that's the end of the show. But they don't want to end the show. So therefore it means that they would have, what is the probability of either B or C being open, given that you've chosen A? And of course, they don't want to open something which they know as containing the right answer, right? Because if they open a third one which actually has a crore rupees behind it, that also ends the show. So how do you put that in? And then therefore you get probability of B given A is half and probability of C given A is half. And therefore you then recalculate that on the basis of this, and you get probability of C is 2/3, while the probability of A is 1/3, and therefore you switch. Intuitively, you can think about it this way, which is that a priori, meaning everything being flat, all three are equal, and therefore it's 1/3, 1/3, 1/3. The person behind the presenter, or the demon or whatever, the god behind the machine knows the answer, and they have chosen one of the two. Of the two that you didn't choose to be the one that they have opened, right? So that probability still remains 2/3, right? Everything from, so imagine thousands of doors. So you can see that if instead of 3 doors there were 100, it would make even more sense to switch to some other thing, right? Because the point being that all the probability that was in B and C put together still remains the same. All you have been removed, in fact, the uncertainty that B was the right answer has been removed. So in fact, you should be even more willing to switch, because that entire sum of 2/3 has now descended on the one unopened door which you haven't chosen. Okay, because if A was right and they had opened it, then you have won. But the fact that they didn't open A should tell you something. Okay, so this is therefore a way of converting reasoning. So what I am doing right now is logical reasoning, right? I'm saying, oh, he must know this, he must know that that is not the case, and so on and so forth. But as soon as you put numbers on it, you get a very exact answer as to how to do this. Right? So what Bayesian reasoning therefore allows you to do is to just as soon as you know that something can be represented numerically, it immediately gives you ways of reasoning which are very, very powerful. Of course, not in every situation will you get something that's such a clear win, but it tells you that just numerical representability gives you a lot of information. Okay, so the take-home lesson is that knowing something is representable as a number is sometimes enough. It should be our first starting point. And if you're doing any kind of data analysis, you should start from these very general principles. Meaning, can I represent something as a number or not? And if it is representable as a number, what kind of patterns should you be able to deduce immediately on the basis of that? And symmetry and scaling principles are typically used for that purpose. So symmetry principles will tell you in the surprise lottery case that there is no symmetry will tell you that at the beginning for you, the symmetry is threefold, meaning all three are equally alike. But for the presenter who knows the right answer, the symmetry is bifold. They know which one of those two is the empty one, so it's only 50%, right? So just from symmetry principles alone, you can also get the same answer. So Bayesian reasoning is just a way to codify that symmetry. Of course, everything that we have done so far is based on this idea that the dimensions are, broadly speaking, linear, meaning that they are quantifiable variables which go from 0 to infinity or whatever. Right? So, but often in the kinds of data that people are beginning to deal with in network situations, the variables themselves may not be linear, they might be non-linear variables.
What do you mean by cardinal dimensions?
Meaning they are continuous and go from 0 to infinity. Right? Ordinal dimensions would be like your partial ordering that I had before, but you can't put a number. So it's not going from 1 to 3, 4. It's just something is more than something else and more than something else.
So a linear dimension which can be represented as a continuous.
Yes. So it's 0 to infinity. So that's what I'm saying, that as soon as you know that something is representable as 0 to infinity versus A is bigger than B and C, that it gives a lot of information. Okay. Now a typical phenomena in network situations is what's called Zipf's law, and a more general version of that is the small world effect. Right? Zipf's law basically says, it was first discovered for word frequencies. Right? So if you plot the frequencies of how many times a given word appears in a corpus, then, and you find the highest ranking word, typically in English it would be the, right? Then you find the frequency at which the next word comes, and then the next, and so on and so forth. What Zipf pointed out is that, broadly speaking, it's doubled. That is to say that given a rank n and a rank n plus 1, the ratio of n to n, the frequency of word of rank n to a word of rank n plus 1 is 2. So it occurs twice as often. So the occurs twice as often as the next one, and so on and so forth. Until, of course, it bottoms out at 1, right? Because if a word never occurs, then it doesn't exist. So already it tells you, because the in some corpus of million words came around 65,000 times, which, if you think about it, is what, 2 to the power 6, so 2 to the power 16. Right, so there are essentially 16 ranks.
So is this to do with the way the English language is structured?
So what it turns out is that this is, it is, meaning it's not particular to English, first of all. Okay, what Zipf's law suggests is that, again, like companies, so the same thing happens if you look at company revenues, if you look at friendship. So if you look at Facebook friendship, so how many people have how many friends, of course, Facebook caps it at the other end, right? So the minimum is 0, the maximum number of friends you can have is 5,000, right? And that's because they don't want this winner-take-all situation, Unlike Twitter, where people can have millions of followers, Facebook caps your friends at 5,000 because they don't want a few people to suck up all the friendships. No, there is a strong reason. Their business model is based on me influencing you to buy something. So if I have 1 million friends, you can't influence me. And it's not clear if I can influence you, because it's one thing. I don't think buying decisions are necessarily driven by people who have lots and lots of friends. So these are empirical questions. Okay? So therefore there are systemic reasons why you should design, how to design a friendship network to do what you want it to do. Okay? But be that as it may, it scales. So the number of people who have 1,000 friends will be half the number, whatever. There will be some factor, and that factor is the scaling law there. Right? So in the case of words, it's 2. So rank n plus 1 is half as often as rank n. Now in the case of friendship networks, I don't know what that scale would be, but let us say that there is some number S, which is the ratio of the number of people who have, let's say, n 1,000 friends divided versus people who have, let's say, 100 friends. Okay, so you can do powers of 10, however, and that number will be the scaling law of that network. Okay, it turns out that many such things, like lots and lots of variables. So if you look at neural connections, they also have similar kinds of laws. And it's very easy to generate those kinds of small scale-free phenomena. A very simple way is what's called preferential attachment. Meaning, if the probability of a new node in the network being attached to one of the old nodes is proportional to the current link strength of that network. So given that I have 1,000 links already, if the probability that I will get a new link is proportional to the number of links I already have, that will immediately generate for you a Zipf's law type of network.
You want to be friends with the person who has no number.
You may want to be, or it may be easier. So for example, if you look at airline, so if you want to design an airline network, you want to do it in hub and spokes. So obviously, once you have developed a hub, so let's say Jet has developed a hub in Bombay, it's so much easier for them to get a new route out of Bombay than out of other places. Because again, there are fixed costs and large fixed costs attached to developing a new hub. Yeah.
Is there a minimum n before which this won't apply?
So there are many, so there are situations where all those kinds of things, there are, you might say, called regimes, right? So below an n, it doesn't work that way, above an n, it doesn't work that way. But the band in which that works will still be that scaling law. I mean, this is very common. Okay, but unfortunately, it's not explanatory, precisely because it arises out of so many different mechanisms that it's not clear if it explains anything. A slightly better thing is what's called the small world effect, right? So famous 6 degrees of Kelvin example, right? So how many links do you need to go from one end of a graph to another? And often many graphs have much smaller lengths than you would think, right? So let's take friendship again before Facebook. Okay, so in the real world, most of us have maybe at most 100 friends. This is a lot. And if you had to talk to 100 of your friends every day, you wouldn't get anything else done, right? So which is to say that if you think about intimate relationships, it may be 20, 30. Even in terms of acquaintanceships, it might be 1,000 at most. Okay, in the pre-Facebook world. So if you think about the number of steps, so if you think about it in a linear way, right? So as a regular graph, the world has 1 billion people, approximately. 10 to the power, now more like 10 billion, but broadly speaking, 10 to the power 9 people. And if you have 100 friends, or even 1,000 friends, if everybody had 1,000 friends, but in a regular linear measure, it would take a billion divided by 1,000, so 10 to the power 6 would be the average distance between 2 points, right? Because I would know 1,000 people, so to know somebody at random, you would have to cross 1,000 some number of times. And again, it's not that hard to do this estimate. It'll basically take the ratio of the size of the network to your friendship, average friendship size, right? So which would be million steps between two people. But 6 degrees of freedom tells you that there's only 6 links. So essentially you're getting a huge win over what a linear model would predict. And the reason is because in a small world network, it's not that some people have lots and lots of friends. That's not how it's going to work. So just imagine a situation where some people have lots and lots of friends. That will only make it, except in situations where there's some person who's universally known, right? So, I don't know, Sachin Tendulkar, somebody like that in India, everybody knows. So if everybody was friends with Sachin Tendulkar, then we would all know each other through 2 steps. But unfortunately, that's not the way it happens, right? We all know Sachin Tendulkar, but Sachin Tendulkar does not know us, to our great dismay. Okay? And therefore, because these are directed graphs, the number of, having some people who know a lot of people doesn't make it much easier. Instead, what you need is the pattern of connections, and in particular, you need networks in which the distribution of connections is not localized. Okay? Or to put it in a geographical setting, it's not that I have a lot of connections that makes it easier for you to connect to me, through me, to somebody in the United States. It's the fact that I have lots of connections in the United States, right? So if there are people who have well-distributed connections, so somebody who has lots of friends in other parts of the world, and then to go from me to somebody who lives in Papua New Guinea, it's much more important that I have some anthropologist friends than if I have lots of friends. So that is a radical new insight, right? It's saying that it's the distribution patterns which are not local and therefore not linear, which really tell you how network size is going to scale. Okay? And again, in the brain, all you need is a few long distance connections and stuff happens which otherwise would be very hard to do. So in that sense, the linear model, if it's replaced by a network model, let's say that the dimension itself is a nonlinear entity, then you would expect Zipf-law-like behavior in all of those networks, right? And it'll be interesting to find out, and this would be, Anand and I have talked about it, right? If you collect all the data across all the, so imagine a metadata repository which had all kinds of, data of all kinds of data. What would be interesting to find out is that also scale-free, meaning that the data of data itself is distributed across a very few set of models. My guess would be it is. Meaning that if you take linear models, things where distances scale linearly, other models which are scale-free, and so on and so forth, my bet would be that a great deal of data of all kinds falls into a relatively small set of data categories. But that's just a hypothesis. So which is to say that the world that we live in doesn't, across sectors, doesn't generate data randomly. Okay? And that is the meta version of what I started with earlier, right? Which is that we are not just that there are patterns, that there are patterns to the patterns, and so on and so forth. Okay, and this is the kind of stuff that we'll be, or at least some of the things that I'll be talking about on Saturday. Okay. we don't have that much time, but let me try to briefly go to stories away from numerical measures to story type measures. Right? And so one question would be, why do we have stories? Right? And of course, stories are very entertaining, so there's no other reason to have stories besides the sheer joy of having stories. But be that as it may, if you want to, monetize stories, which people seem to want to these days, why, under what situation, is a story a better framework than a number? Right? As I was mentioning, people have shown that stories come in certain patterns. And this is a very interesting book. It's called The 7 Basic Plots, Why We Tell Stories. Right? So these are the stories broadly and across the world seem to come in a very small set of patterns. In fact, according to Booker, 7. The largest number that I have seen is, I forgot the name of the person, but this is somebody, I think is about 140, which is minuscule by our modern big data standards. Right? So meaning there are not that many different kind of stories that there are. Okay. And the basic story types, according to Booker, are these, right? Rags to riches, the quest, voyage and return, comedy. So that if you go back to those 3 sentences that I wrote, right, about Ramesh, you can see that they actually fall quite well into the story types here. Right? So there's the monster, which was the dragon. Then there is the quest, which is being able to get home. So all of these. So what it shows you is that our base, the way we organize our lives, falls into these very, very sharply limited set of story patterns. And so what is a story pattern? It's a sequence of stable events, meaning that me turning into a dinosaur and eating all that is a stable event, right? I don't shift back and forth from dinosaur to human. It's not that often. And each event is a non-accidental mapping of 2 contexts. Right? That's the important thing. And the story 4 is you might call the momentum of the story is driven by each event sort of forcing the next one.
Can you explain the first one?
Which one?
The first one, each event
is a non-accidental. So meaning that in the story, the connector between 2 events, right? Or rather, the connector between, an event is a connector between 2 entities, which is a non-accidental thing. So for example, me turning into a dinosaur is a non-accidental, I won't even have mentioned it if it was. So for example, of all the things that I was doing at that time, I was walking, I was, so let's say that in a 5-minute period in which at the beginning I was a human and at the end I was a dinosaur, zillions of things happened, just to me, forget the rest of the world. But of those, the only things that I've isolated in this story is that turning into the dinosaur. And that's the non-accidental nature. So the principle of context change is that the story moves from one frame to the next if one of the 2 following happens, right? The 2 agents. So suppose that a story is an interaction between 2 people, Romeo, Juliet, or so that's the tragedy version of it. So you can have Romeo, Juliet, you can have Arjuna and Karna if you want the antagonistic version, which is also kind of like Romeo and Juliet in other ways. So if you have 2 agents, so if the 4 possibilities are the 2 agents value each other positively, but they do not form a unit. So you have 2 agents, so plus minus. So you either have antagonistic or agonistic relations, and you have either they form a unit or they stay separate. So there are 4 possible choices. Right? So they value each other positively, but they do not form a unit. They value each other negatively, and the weaker one wins. The two agents have mixed opinions, but they get to have the same valuation, or positive or negative. These are essentially the only ways that the story can move.
A weaker one means the person who is more negative. Could be. The two agents value each other negatively, and the weaker one. How we define weaker over here?
Whatever that is. I mean, let's assume that David and Goliath, right? So, however you value the positive or weaker, and they are antagonistic to each other, and the weaker one wins. If the stronger one wins, it's not a story. Here's the, if David and Goliath is not a story if Goliath wins. I mean, this is a very simple thing. I mean,
Because it's not non-accidental.
Exactly.
It's a very
that's the default assumption about the world, right? A story makes sense only if it is non-accidental. Okay? So to summarize, I mean, if you want to put it all together, you can represent the world using numbers, and you can represent the world using stories. But what about numbers plus stories? Right? And that's where images come in. So you include numbers within stories as images. And that's what really a great deal of whether journalistic or science or whatnot writing is about. Okay, that we include, unless you are a theorist, so if you are somebody who is trained in mathematics and you can read numbers like stories, that's a different matter. But most of us are not. But that's really what equations are. Equations are numbers stored by stories as well. Okay, so numbers do space well, right? It's very easy to measure spatial things. Stories do time well, because temporal progression driven by the momentum of the story is really what we experience in a sense time as stories, cognitively, whether as opposed to the real world. Okay, so if you combine the two, you get stories with numbers. So let's start with that. Any questions?
I have one about the earlier slide that you talked about the zip. What is it?
Zip law.
Zip. Now, when you mentioned the example of words, how often, to ask what kind of questions would you do with
This kind of-
computation, if not particular to that language itself?
See, what it tells you is Zipf's law, because you can't, for example, if Shakespeare obeys Zipf's law and I obey Zipf's law, but we write radically differently, then you don't really, you can't do interesting analyses on our respective writing styles on the basis of Zipf's law, right? But so that is one of the critiques of this kind of scale-free network Zipf's law behavior, is that if it applies to everything, it simply is not either predictive or explanatory of anything. Okay? So what is happening now is more fine-grained kinds of analysis. So which is to say that if the default, just as in the linear regime, A is proportional to B, whatever B, or A is proportional to some simple linear or square root, whatever combination of A and B is the norm. It's only when it's the deviation from that where all the interesting stuff happens. So in the same way, we would have to ask, what is the deviation from Zipf's law in the case of, so if you see somebody who has systematically deviated from Zipf's law, you know that they have made some explicit effort to do so. And it'll be interesting to find out, because especially if you look at Sanskrit literature where wordplay was very common, it might be interesting to find out if there are systemic deviations from Zipf's law there. Right? And similarly in other traditions where just the stylistic patterns were extremely important. Modern literature broadly doesn't care about that so much, but traditional literatures do. And another kind of thing, and I'm sure somebody has done it, right? If you look at poetic styles, so you look at, say, iambic pentameter or couplets or stanzas, does that structuring, which is to say giving a certain explicit form to the poetry, what does that do to word frequencies? Is it correlated in some way? Those are the things. All right, thank you. We'll be back next week. So what I'm going to do is, please, if you haven't signed up for a project, send me an email, and I will both introduce people in the same project to each other and create a group for each